Let's talk about the intermolecular interactions. We all know that intermolecular distance for gases, liquids, and solids are different. You can walk in the air, the gas. You may swim in the liquid, water. But you cannot even put a finger into a solid, because the solid is very dense. The intermolecular interactions in solids are strong. The phase of a solid, liquid, and a gas can be changed if energy is supplied or released. A solid can be fused to liquids and further vaporized to gas. The intermolecular interaction in a solid is reduced during this process. The intermolecular interaction in a gas is quite weak. The reverse process occurs if we cool the gas down. It turns into a liquid and further into solid. The intermolecular interactions takes over. The molecules are bound tightly. Now, let's use liquid as an example so that we may have a deep understanding on the intermolecular interactions at the molecular level. The physical property of the liquid are associated with the nature of the intermolecular interaction, of course, and the properties of liquid are shown here. Vapor pressure, for example, the pressure of vapor above the liquid. The vapor comes from the liquid. There are always molecules escape from the liquid phase. But if the intermolecular interaction in liquids is strong, the molecule will not leave easily. The intermolecular interaction can also be used to understand the boiling point, surface tension, and viscosity of the liquids. Generally, for liquids, the stronger the intermolecular attractions, the higher the boiling point. The greater the surface tension, the higher the viscosity, and the lower the vapor pressure. Most intermolecular interactions originate from the polarity of molecules. Even the molecule is not polar. It may be polarized. The larger the molecule, the larger the polarizability. We should always care the polarizability and the polarity of the electronic charge cloud, not the mass of the molecule. If the molecule is polar, the charge distribution of the molecule is not equally on its atoms. There will be dipole-dipole interactions. As shown here, they end with the negative charges attract the positive ends of another molecule, and the whole molecules are bound through this electrostatic interaction. The electrons in the molecule are in constant moving at a particular instant, and a symmetric distribution of charges may form in the molecule. One end of the molecule is more negative and the other more positive. This polar molecule can induce the molecule around into polar molecules too. Then there will be dipole-dipole interaction between these polar molecules. In general, London dispersion forces are most attractive when the molecules are larger and always contribute to the molecular interactions. Hydrogen bonding is another type of dipole-dipole attraction between a hydrogen atom covalently bonded to a very electronegative atom, such as a nitrogen, oxygen, or fluorine atom, and another very electronegative atom, usually nitrogen, oxygen, or fluorine atom. The hydrogen atom is positively charged, will attract the negatively charged atoms, and a strong bonding in between forms. The strength of hydrogen bond is stronger than that of a dipole-dipole interaction, but far less than the strength of covalent or ionic bonding. Question: are the molecules polar or nonpolar? These molecules are methane and its derivatives with tetrahedron structure. We can analyze the polarity of every single bond in the molecule to deduce the polarity of the whole molecule. For simplicity, the bond of hydrogen and carbon is assumed to be nonpolar because the polarity of this bond is low. Now, the three molecules with chlorine atoms are polar. Tetrachloromethane is nonpolar because the polarity is cancelled off due to symmetry.